Good day, students. The third lesson in Module 6 is about chemical reactions and chemical equations. So what is a chemical reaction? It is a process in which the substances are changed into new substances. So there is chemical change. New substances are formed. The chemical composition of a substance is changed into another. So new substances are formed in a chemical reaction. Chemical equation, on the other hand, uses chemical symbol to show what happens during a chemical reaction. So this is what a chemical equation looks like. We have here an arrow. On the left side of that arrow are the reactants, and on the right side of that arrow are the products. So reactants are the starting materials of the reaction. Products, on the other hand, are the new substances formed during the chemical reaction. Now, the numbers which appear before the chemical symbols of each of the reactants and products are called coefficients. No? So you have our 2 here, coefficient for hydrogen gas. Here, since we cannot see any number, there is 1 in there, okay? So we have 1 coefficient for oxygen gas, and we have a 2 coefficient for water. Now, balanced chemical equation obeys the law of conservation of mass and energy. This means that the mass of our reactants, although the reactants are changed to or converted to products, our products will have the same mass as that of the reactants. The total mass of the reactant is equal to the total mass of the products, okay? So matter is neither created nor destroyed by ordinary chemical means, okay? We have here 70 kilos before. After the chemical reaction, it should still be 70 kilos, for example. Now, how do we balance chemical equations? Here, as I've said in the previous slide, the number which appear before the chemical symbol of the reactants and products are called coefficients. The numbers, on the other hand, which appear after each chemical symbol are called subscripts. So again, how do we balance chemical equations? What we do is we make use of coefficients. Okay, we should never change the subscripts of chemical formulas. To balance chemical equations, we will make use of coefficients. Now, we balance the different types of atoms one at a time. And we balance first the atoms of elements that appear only once on each side of the equation, or we start first with the atoms of the element with the larger atomic number, okay? So remember this. We start with atoms of elements that appear only once, or we start the element with a larger atomic number. Then we balance hydrogen and oxygen atoms after all the other elements have been balanced. Now, if some coefficients are not written in whole numbers, like for example, when you try to balance the equation, you use fractions or decimals. What you do is, to make the coefficients whole numbers, we multiply the entire equation by a factor that could make the coefficients in the balanced equation whole numbers. So let's have an example. In this equation, we have nitrogen gas which reacts with hydrogen gas to form ammonia. So we have, what are the elements here? We have nitrogen and hydrogen, okay? So on the left side of the equation, we only have one nitrogen atom. Same with the nitrogen atom on the right, we also have one of that nitrogen element. For the hydrogen, we have this one on the left side and another one on the right side. So in this case, we start with the atom of the element with larger atomic numbers. In this case, the element with the larger atomic number is nitrogen. Okay, so on the reactant side, we have how many nitrogen atoms? We have 2. Okay, since we cannot see any number here, that means there is 1. So we multiply the coefficient with the number in the subscript to get the number of atoms of that element. So we have 1 times 2. Therefore, we have 2 nitrogen atoms on the reactant side. On the left side, we have, since we cannot see any number here, that means there is only 1 in the subscript and also another 1 in the coefficient. So we multiply 1 by 1 in here. You have 1 multiplied by 1. We have 1 nitrogen atom. So what do we do here to balance the nitrogen atoms in the equation? We have to put a coefficient 2 before the ammonia chemical symbol. So now we have 2 times 1 in here. We now have 2 nitrogen atoms on the right side of the equation. So now we have balanced the nitrogen atom. Next, for the hydrogen atom on the left side of the equation, we have, since we cannot see any number here, so there is 1 in here. So we have 1 times 2, we have 2 hydrogen atoms on the left side of the equation. Whereas on the right side, we have 2 times 3. So what you do again, we multiply the coefficient with the subscript of each of the elements. We have 2 times 3, we have 6 hydrogen atoms on the right side. So therefore, the number of hydrogen atoms is not yet balanced. So what we do is we add a coefficient 3 for hydrogen. Because when we multiply 3 by 2 here, we get 6. So now we have balanced all the atoms in this equation. So this is now our balanced chemical equation. Another example, we have sulfur reacted with oxygen to form sulfur trioxide. So in this equation, we have sulfur. So we have sulfur and, where is it now? Sulfur and oxygen atoms. So on the left side of the equation, we only have 1 sulfur atom. Same with the sulfur atom on the right side of the equation. For the oxygen atom, we also have 1 on the left and 1 on the right. So here we start with the atom which has larger atomic numbers. So in this case, we have sulfur. Okay, so in this equation, we only have 1 sulfur atom on the left side of the equation. We have 1 in here and another 1 in the subscript. So 1 times 1, we have 1. On the right side, we have, since we cannot see a number here, that means there is 1. Same with the subscript here, we have a 1 here. So 1 times 1, you also have 1 sulfur atom on the right side of the equation. So we move to oxygen atom. On the reactant side, we have, this is 1 here. 1 times 2, we have 2. On the right side of the equation, we have 1 times 3 in here. So there is 3 oxygen atoms on the product side. So therefore, the number of oxygen atoms in the equation is not balanced. So what do we do to balance the number of oxygen atoms in the equation? We use the, what's that called? Least common multiple. So that's 6 for 2 and 3. So to make this 6, we have to put a coefficient 3 in here. So that's 3. So what happens now is we have 3 times 2. The number of oxygen atoms on the reactant side becomes 6. Okay, so to make this number of oxygen atoms on the right side 6, we have to add a coefficient 2. You multiply 2 by 3 in here. This now becomes 6. Okay, so we have now a balanced chemical equation. So let's recap. We have sulfur and oxygen. For the oxygen atom, we have 6 and on the left side of the equation and 6 on the right side of the equation. However, when we add the coefficient 2 in here, we multiply this with number 1 subscript for sulfur. The number of sulfur atom on the right side now becomes 2. Okay? Whereas on the left side, we only have 1. No? So when we add the coefficient 2 in here, the number of sulfur atoms now is not equal on both sides of the equation. So we have to add a coefficient 2 for sulfur on the left side of the equation so as to balance now our equation. So this is now the balanced chemical equation. Another example, we have hydrogen gas reacted with oxygen gas to form water. So in this equation, we have hydrogen and oxygen. On the left side, we have one hydrogen atom and one on the right side, and one for oxygen, and on both sides of the equation. So where do we start? We start with oxygen because it has a larger atomic number. In the reactant side, we have 1 times 2 in here, we have 2 oxygen atoms. On the product side, we have 1 times 1, so we have 1 oxygen atom. Now we don't have a balanced number for oxygen atom in the equation. So what do we do is we add the coefficient 2, because when we multiply 2 by 1 here, you'll have 2 oxygen atoms. Okay, so now we balance the number of hydrogen atoms. On the product side, we have 2 times 2, this is 4. Whereas on the reactant side, we only have 1 times 2, so this is 2. So what do? We have to add a coefficient 2 for hydrogen, because when we multiply 2 by 2 in here, we get 4. Okay, so we have now, is that balanced already? We now have a balanced chemical equation. Another example, we have calcium oxide reacts with water to form calcium hydroxide. So in the equation, we have calcium, oxygen, and hydrogen. Okay, here our element to the largest atomic number is calcium. So we start balancing calcium atom in this equation. On the left side, we have 1 times 1. So we only have 1 calcium atom on the left side. On the product side, we have 1 times 1. So we also have 1 calcium atom. So we now have balanced number of calcium elements or atoms in the equation. Now we move to oxygen, the second larger atomic number. And the reactant side, we have 1 times 1 in here, so you have 1. And we also have another oxygen atom here, so 1 times 1. So we have 1 plus 1. We have 2 oxygen atoms on the reactant side. On the product side, if you see this subscript outside the parenthesis, you have to multiply this with the subscript of each of the element inside that parenthesis. So in this case, you have 2. You multiply this with the subscript 1 of oxygen. So we have 2 times 1. We have 2 oxygen atoms on the product side. So we have a balanced number of oxygen atoms in the equation. Now we move to the number of hydrogens. On the reactant side, we have a coefficient 1 in here and a subscript 2. So we have 1 times 2. We have 2 hydrogen atoms on the reactant side. On the product side, we have 2 times 1. So we have 2. By the way, after multiplying this number outside the parenthesis with a subscript of the elements or atoms inside the parenthesis, you have to multiply that also with the number of coefficient in here. But since this is only 1, so when after multiplying this one, that's the same answer. No? So you have 2 times 1, that's still 2 because our coefficient here is only 1. Okay, so we have balanced number of hydrogen atoms in the equation. So since all of the elements here have the same number or number of atoms on both sides of the equation, this equation is already balanced. We don't have to add coefficients anymore. Okay, let's have some more examples. Ammonium dichromate decomposes to form nitrogen gas, water, and chromium oxide. So in this equation, we have nitrogen, hydrogen, chromium, and oxygen atoms. Okay, so in this equation, the element with the largest atomic number is chromium. So we start balancing chromium. On the left side of the equation, we have 2. Our coefficient here is 1. So 1 times 2, we have 2. On the product side, we have 2 times 1 in here. So we have 2. So our chromium atoms on both sides of the equation is equal. The number, I mean. Next, what do we balance next? We look at the number of what? Number of oxygen atoms. So on the reactant side, we have 7 times 1 in here. So we have 7 oxygen atoms. On the product side, we have 3 times 1. We have 3 plus 1 times 1 here. We have 1. So 1 plus 3, we have 4 oxygen atoms on the product side. So to make that balance, we have to put a coefficient 4 in here, because when we multiply 4 times 1 in here, we get 4. Then plus 3 on the chromium oxide oxygen atom. So we now have 7. Okay, so this becomes 7. So we have a balanced number of oxygen atom on the equation. Next, we move to nitrogen atom. On the reactant side, we have 2 times 1 is 2 times 1 on the coefficient, so we have 2. On the product side, we have 2 times 1 in here. We also have 2. Okay, so we have a balanced number of nitrogen atoms in the equation. Next, the last one is hydrogen. On the reactant side, we have 2 times 4 is 8. Times 1 in the coefficient, we have 8. On the product side, we have 2 times 4, we have 8. Okay, so the hydrogen atoms on both sides of the equation is balanced. Since all the atoms in this equation are balanced, so we now have a balanced chemical equation. Another example. Zinc reacts with hydrochloric acid to form zinc chloride and hydrogen gas. So in the equation, we have the elements zinc, hydrogen, and chlorine. Okay, where do we start? Here, the element with the largest atomic number is zinc. So we start balancing the number of zinc atoms in the equation. On the left side, we have 1 times 1 in here, so you have 1 zinc atom. On the right side of the equation, we have 1 times 1, so we also have 1 for zinc. Next, we move to chlorine, the next larger atomic number element, with the larger atomic number. On the left side of the equation, we have 1 times 1 in here, so you have 1 chlorine atom. On the right side of the equation, we have 2 times 1, so we have 2 chlorine atoms. So what do? We have to multiply or put a coefficient 2 in hydrochloric acid, because when we multiply 2 by 1 in here, this becomes 2. Okay. Lastly, we have hydrogen. On the left side of the equation, we have 2 times 1. We have 2 hydrogen atoms. On the right side, we have 2 times 1 in here. So we have 2. Okay? So now we have a balanced chemical equation. Another example. Sodium reacts with water to form sodium hydroxide and hydrogen gas. So in the equation, we have sodium, hydrogen, and oxygen. The atom with the largest atomic number is sodium. So we start balancing sodium. On the left side of the equation, we have 1 times 1 in here. So we have 1 sodium atom. On the right side, we have 1 times 1. So we have 1. Okay. Next, oxygen. On the left side, we have 1 times 1. So we have 1. On the right side of the equation, we have 1 times 1 in here. We also have 1. Next, 4 hydrogens. On the left side of the equation, we have 2 times 1 in here. We have 2. On the right side of the equation, we have 2 times 1 is 2. Then we have another one here. 1 times 1 is 1. So 1 plus 2 is 3. We don't have a balanced number for hydrogen atoms in the equation. So what do? We have to add, what should we do? We have to add 2 for sodium hydroxide and water. Okay? So when we put a coefficient 2 in here, we have 2 times 2. This becomes 4. Then multiply this 2 by 1 with a subscript here. So this becomes 2 plus 2. We now have balanced number of hydrogen atoms in the equation. Okay? So this is now the balanced chemical equation. By the way, when we put 2 in here, the number of sodium atom has not changed, no? So we have 2 times 1, this becomes 2. So we also have to put 2 in the sodium atom on the reactant side, okay? And this is now the balanced chemical equation. Okay, next example. Iron plus reacts with hydrochloric acid to form ferric chloride and hydrogen gas. So we have iron, hydrogen, and chlorine. On the left side of the equation, we have 1 iron, because we have 1 times 1, it's 1. On the right side of the equation, we have 1 times 1, so we have 1. Next, we move to chlorine. On the left side of the equation, we have 1 times 1, so we have 1 chlorine atom. On the right side of the equation, we have 3 times 1, we have 3. So we don't have a balanced number for chlorine atoms in the equation. What do? We have to add a coefficient 3 in hydrochloric acid. Okay, so that becomes 3 times 1 in here. This becomes 3. Okay, that's balanced number. Next, for the hydrogen atoms, on the left side, we have 3 times 1. We have 3 in here on the reactant side. On the product side, we have 2 times 1. We have 2. So what do? To make that balance, we can add a decimal. 1.5 times 2 is also 3, right? But after adding that decimal, we have to multiply the whole equation by a factor that could remove this decimal or make this a whole number. So in this case, we have to multiply this by 2. So what happens now? Okay, so when we multiply the equation by 2, so we have 2 times 1. What you do is you multiply 2 with the coefficients, no? Coefficients of the chemical symbols in the reactants and product side. So you have 2 times 1, we have 2. 2 times 3, we have 6 for hydrochloric acid. 2 times 1 in here, we have 2 for ferric chloride. And then 2 times 1.5 for hydrogen gas, that becomes 3. Okay, so this is now the balanced chemical equation. We have 2 for iron on the left side, same on the right side. For chlorine, we have 6 times 1, so we have 6. In the product side, we have 2 times 3, we also have 6. For the hydrogen, we have 6 times 1, we have 6. And on the product side, we have 3 times 2, we also have 6. So we have now a balanced chemical equation. Now for combustion reactions, so we balance first the carbon followed by hydrogen and lastly oxygen atom. Okay, so we have carbon, hydrogen, and oxygen. On the reactant side of this equation, we have 1 carbon atom. We have 1 times 1, so we have 1. On the product side, we have 1 in here times the 1 in the coefficient. So we also have 1 carbon atom. Next, for the hydrogen, we have 4 times 1 in the coefficient. We have 4. On the product side, we have 2 times 1 in the coefficient. So we have 2. So what do we do to balance the number of hydrogen atoms? We have to add a coefficient 2 in here. Okay, so 2 times 2, we now have 4 hydrogen atoms on the product side. Then we now balance the number of oxygen atoms. So to balance the number of oxygen atoms, we have to look at the uh, number on both sides of the equation first. So we have 2 times 1, we have 2. On the product side, we have 2 times 1 in the coefficients, we have 2. Plus, here we have 1 times 2, we have 2. So 2 plus 2 is 4. So to balance the number of oxygen atoms, we have to add the coefficient 2 for oxygen in the reactant side. You have 2 times 2, we now have 4. Okay? So now we have the balanced chemical equation. Okay, next example. Again, we start balancing the number of carbon followed by hydrogen and lastly oxygen. Okay, so a combustion reaction has this fuel plus oxygen. Oxygen is always found in the reactant side, and on the right side we have our oxide, carbon dioxide or monoxide depending on the type of combustion reaction, and we also have our water. Okay, so on the reactant side, we have how many carbon atoms? We have 2 times 1 in the coefficient, so we have 2 carbon atoms. On the product side, we have 1 times 1, so we have 1 carbon atom. So what we do here is we add the coefficient 2 for carbon dioxide. Okay, because when we multiply 2 by 1, we now have 2 carbon atoms. Okay. Next, we balance the number of hydrogen atoms. On the reactant side, we have 6 times 1 in the coefficient. We have 6 hydrogen atoms. On the product side, we have 2 times 1 in the coefficient. So we have 2 for hydrogen. So to balance the number of hydrogen atoms, we have to add 3 in the coefficient. Okay? When we multiply 3 by 2, we now have 6. Lastly, we balance the number of oxygen atoms. On the reactant side, we have 2 times 1. So we have 2 oxygen atoms on the reactant side. On the product side, we have 2 times 2 is 4 plus 3 times 1 is 3. So, how do we balance? Therefore, we have how many oxygen atoms on the right side? We have 4 plus 3, we have 7. So, to balance the number of oxygen atoms, we can add a 3.5 in the oxygen on the reactant side because when we multiply 3.5 by 2, we have a 7. But since we have a decimal here, we have to multiply this whole equation by a factor that could remove that decimal in the coefficient. So here we can multiply the equation by 2. So what happens now? We have 2 times 1 in the coefficient there. We now have a 2. Then 2 times 3.5 will have 7 coefficient for oxygen. And for carbon dioxide, we have 2 times 2. We have a 4 in the coefficient. Lastly, for water, we have 2 times 3. So the coefficient here is 6. Another example. This is still a combustion reaction. So again, we start with carbon followed by hydrogen and lastly oxygen. So on the reactant side, we have 3 times 1, so we have 3 carbon atoms. On the product side, we have 1 times 1, so we only have 1. So to balance this, we have to add a coefficient 3 in here. So now we have 3 carbon atoms on the right side of the equation. Next, For the hydrogens, we have on the reactant side 8 times 1, we have 8 on the reactant side. On the product side, we have 2 times 1, so we have 2. So therefore, we have to add a coefficient 4 in water molecule, because when you multiply 4 by 2, we now have an 8 hydrogen atoms on the product side. Lastly, for the number of oxygen atoms, on the reactant side, we have 2 times 1, so we have a 2. On the product side, we have 3 times 2 is 6, plus 4 times 1 is 4. So we have 10 oxygen atoms on the product side. Therefore, we can add a coefficient 5 for oxygen here. When we multiply 5 by 2, we now have 10 number of oxygen atoms on the reactant side. Okay, so we have a balanced chemical equation now. Okay, so we have different types of chemical reactions. We start with combination reaction. When we say combination reaction, this is a reaction of 2 or more elements to form a more complex substance. So in general, we have, for combination reaction, we have A and B. They combine to form a more complex AB substance. Okay, that's in general. For example, here we have nitrogen and hydrogen gas. They react or combine to form ammonia, which is more complex than the starting material. Another example of combination reaction, we have sulfur reacting with oxygen to form sulfur trioxide. If you have observed, we have again 2 or more in the reactant side, and we have 1 on the product side. The reactants combine to form a more complex substance. Another example, we have water reacting with oxygen to form, hydrogen reacting with oxygen to form water. And we have calcium oxide plus water reacting to form a calcium hydroxide substance. Okay, so these are example of combination reactions. Another type of chemical reaction is decomposition reaction. This is a reverse, or an opposite of the combination reaction. Here, simpler substances are formed from a bigger substance. So in general, a decomposition reaction has this equation. We have an AB. This is the bigger substance. On the product side, now we have the simpler substance. We have 2 or more substances formed from a single substance, or a bigger substance. Like, for example, we have calcium carbonate. It decomposes to form calcium oxide and carbon dioxide. Another example here, we have carbonic acid. So it decomposes. This is a very weak acid which decomposes instantly to form water and carbon dioxide. Okay. Another example, we have ammonium dichromate, which forms nitrogen, water, and chromium oxide. So these are example of decomposition reactions. We have a bigger substance in the reactant side, and we have simpler substances, 2 or more products formed. Another type of chemical reaction is single displacement reaction. So here, there is displacement of atom or ion from a compound by an atom or ion from another substance. In general, a single displacement reaction has this equation. We have our compound and we have a separate atom or ion. And the atom or ion in this compound is being replaced by this atom or ion. So in this case, what was being replaced? The A here is being replaced with C. So in the product side, we now have our Cb. Recall that in a compound, the first component is our cation, whereas the second one is our anion. Okay, so again, single displacement here, an atom or ion, a separate substance, displaces either the A or the B in a compound. In this case, what was being replaced is the A. So in the product side, we now have our Cb, and then the A is separated. Okay, so AB plus C, we have Cb plus A. Or We could also replace, instead of A, it could be the B that is being replaced by C. So in the product side, we now have A, C, and B is separated or being displaced. So as example, we have first zinc plus hydrochloric acid forms zinc chloride and hydrogen gas. In this case, what was being replaced is the what? The hydrogen. The hydrogen in hydrochloric acid is being replaced with zinc. So in the product side, we now have zinc chloride. So they are the ones which combine, and our hydrogen is being displaced to form a hydrogen gas. Another example, we have copper added to silver nitrate to form copper nitrate and silver. In this case, silver is being displaced with copper. So copper combines with nitrate to form copper nitrate, and silver is being displaced to form a precipitate or silver solid. Another example here, we have chlorine gas, which is reacted with potassium iodide to form potassium chloride and iodine. So in this case, the iodine is being displaced by chlorine to form potassium chloride. So this combines to form potassium chloride. Iodine is being displaced to form a precipitate or a solid iodine. So these are examples of single displacement reactions. Now, single displacement reactions follow the so-called activity series, okay? So for a single displacement reaction to occur, we have to follow this so-called activity series. So we have activity series of metals, I mean. In this, how do we interpret the series? Those metals or elements on the top can displace those elements or metals on the bottom or below them, okay? So a reaction only occurs when the element or the metal on the separate substance are on the top of the series, because they are the ones which can displace those below them, okay? So that is how we use the activity series of metals. Again, only those metals at the top can displace those metals below them. Like for example, we have lithium in the separate substance, and then we have what example rubidium chloride, for example. So in this case, we have a single displacement reaction because lithium can displace rubidium because it is higher than lithium is higher than rubidium in the series. Okay, so there is a reaction forming what? Lithium chloride plus rubidium. But if the reaction is like this, we have lithium chloride plus rubidium. Since rubidium is below lithium, it cannot displace lithium in the reaction. So therefore, we don't have a reaction in here. Okay? So that is how we use activity series. In the first equation, since lithium is the one which will displace rubidium, we have to look at the series. It's above rubidium, so there is a reaction. Lithium can displace rubidium to form lithium chloride, and rubidium is now displaced. Here in the second equation, rubidium, which will suppose to be displacing lithium chloride or lithium in the lithium chloride. No? Again, we refer to the activity series. Rubidium is below lithium, so it cannot displace lithium in the compound. Therefore, we don't have a reaction in here. For halogens, we have this series. Fluorine gas can displace chlorine, which can displace bromine, and which can displace iodine. Okay? Iodine cannot displace bromine, chlorine, and fluorine. So we have to follow this. You have to familiarize the elements in this series of metals and for the activity series for halogens. Okay, let's have some examples. Hydrogen displacement. When you say hydrogen displacement, hydrogen is being displaced by what? Metal, no? Forming hydrogen as one of the products. So what can displace hydrogen? Let's look at the series. Where is hydrogen here? Hydrogen is here, okay? So only the metals from lead up to the lithium, only these elements can displace hydrogen. Copper down to gold cannot displace hydrogen. So we don't have a single displacement or hydrogen displacement in here. Okay, take note of these elements. Only these are the ones which can displace hydrogen in a reaction. So like for example, we have zinc. Zinc plus hydrochloric acid, we can form zinc chloride and hydrogen gas. Again, in hydrogen displacement, hydrogen is being displaced by a metal above it. Okay, and in the process, hydrogen gas is being formed. Let's look at the series if we can see zinc above hydrogen. Where is zinc? Zinc is here, okay? It's above hydrogen, so it can displace hydrogen in the process, forming hydrogen gas. Okay. You can tell whether a reaction has occurred because you can observe some bubbles, okay? That is due to the hydrogen gas being formed in the process. Another example, we have sodium. When you add that to water, you form sodium hydroxide and hydrogen gas. So let's look at the series if we can see sodium above hydrogen. Where is sodium? Sodium is here, okay? So therefore, we have a reaction. Sodium can displace hydrogen. Another one, we have iron. When you add that to hydrochloric acid, we form ferric chloride and hydrogen gas. Where is iron? Let's go back so that we can look at the series. Iron. Where is iron? Iron is here, no? So it's still above hydrogen. Therefore, we have a single displacement or a hydrogen displacement specifically. For metal displacement, again, only those metals above in the series can displace the metal below them. So metal displacement is a displacement of a metal ion in a compound by an uncombined metal. Again, this uncombined metal should be in the higher position in the activity series so that it can displace the metal ion in the compound. So example here, we have copper plus silver nitrate. We form copper nitrate and silver. So we have to see if the copper here is higher than silver in the activity series. Let's go back to the activity series. So here copper is here and silver is below the copper. So therefore copper can displace silver in the equation. So we have a single or metal displacement reaction. Another example, we have iron. When you add that to copper sulfate, we have ferrous sulfate and copper solid. So for this reaction to occur, iron should be higher than copper in the activity series. So let's go back to the activity series. So in this series, we have the iron. Where is iron now? Iron is here. Copper is below here. So therefore, iron can displace copper in the equation. And we have our chemical reaction. So here is an example of the reaction. We have our iron nail. We dip that in a copper sulfate solution. What happens is we form the ferrous sulfate. Here we have the iron sulfate, and then we have the copper metal. Okay, this is the copper metal. Another example, we have tin plus copper nitrate. We form tin 2 nitrate and copper solid. So again, in the activity series, this should be higher than copper for a reaction to occur. For halogen displacement, So this is a displacement of halogen anion in a compound by a halogen. Again, this is the activity series for halogen. So as an example, we have fluorine plus sodium chloride. We form sodium fluoride and chlorine. Fluorine here is higher than chlorine, so it can displace chlorine in this compound to form sodium fluoride, and chlorine is being displaced to form chlorine gas. Now, when we have chlorine, when we put it the other way, we have chlorine plus sodium fluoride. Since chlorine here is lower than fluorine in the activity series, chlorine cannot displace fluorine, so there is no reaction. Another example, chlorine plus potassium iodide. In the activity series, chlorine comes first before iodine, so chlorine can displace iodine. So iodine then is being displaced to form iodine solid. Now, if it's the other way around, if we have iodine plus potassium chloride, since iodine is below in the activity series, it cannot displace chlorine in the compound. Therefore, we don't have a reaction in here. Another type of chemical reaction is double displacement reaction. So here we have exchange of counter ions from two substances capable of dissociating into ions. So there is exchange of ions. Here, A will pair with D because it is cation, and ion, cation, and ion. So of course, cation will pair with an ion. So we have an AD and a CB. Okay, when we write compound, we have to write first the cation part before the anion. That's why we have an AD and a CB. Okay, as an example, we have hydrochloric acid, which reacts with sodium hydroxide to form sodium chloride and water. Okay, so here, this is our cationic part, and this is our anionic. This is our cationic, and this is our anionic. So H plus here will combine with hydroxide to form water. Sodium, on the other hand, will combine with chloride ion to form sodium chloride. Again, we have to put first the cationic before the anionic in writing the compound. So we have different types of double displacement reactions. We start with neutralization reaction. In this reaction, we have an acid and base reacting to form water and salt. So we have acid plus base forming salt and water. As an example, that the previous equation is actually a neutralization reaction. HCl is our acid. This is a hydrochloric acid. Sodium hydroxide is a base. Sodium chloride is a salt formed, and we have, of course, the water molecule. Another example, we have nitric acid plus, this is the acid part. Potassium hydroxide is the base. The salt form is called potassium nitrate, and then we have the water molecule. So again, this is H combining with OH to form water, and then potassium ion combining with nitrate ion to form potassium nitrate. So there is exchange of counter ions. Another type of double displacement reaction is called precipitation reaction. So from the word precipitation reaction, there is precipitate form. No? After the exchange of ions, we have the formation of insoluble or sparingly soluble salt, which we call precipitates. So as an example, we have magnesium nitrate reacting with potassium hydroxide to form potassium nitrate and magnesium hydroxide. In this case, the precipitate form is called magnesium hydroxide. So here, what happens is that the magnesium combines with hydroxide to form magnesium hydroxide, and then our potassium combines with nitrate to form potassium nitrate. Another example, we have silver nitrate reacting with sodium chloride to form sodium nitrate and silver chloride. So here, silver combines with chloride ion to form silver chloride, which is the precipitate form. And then we have our sodium combining with nitrate ion to form sodium nitrate. So in this case, the silver chloride is the precipitate form. So this is the silver chloride formed in the reaction. In precipitation reaction, we actually refer to solubility rules, okay? So as we will know whether precipitates are formed or not after the equation. So here, this is an example of solubility rule. How do we use solubility rule? Here we have nitrate ion. Those compounds which contain nitrate ions are all soluble, okay? So they dissociate. They do not form precipitates. Same with all compounds containing perchlorate ion. They are all soluble. They don't form precipitates. For chloride ion, they are soluble except when they are combined with silver, mercury 1, and lead 2. Okay? So only these compounds are insoluble, or these chlorides are the ones which are insoluble or form precipitate. So silver chloride, no, when silver ion combines with chloride ion, then we have mercury 1 chloride and lead 2 chloride. Okay, again, all chlorides are soluble except when they are combined with silver, uh, mercury 1, and lead 2. Same with iodides. No? They are all soluble except when they are combined with silver, mercury 1, and lead 2. For sulfates, these are the sulfates, they are soluble except when they are combined with silver, lead 2, mercury 2, strontium, barium, and calcium. So, for example, when we have calcium sulfate, this forms a precipitate. No? When we have barium sulfate, you also have another precipitate. Carbonates. Carbonates are insoluble except when they are paired with group 1 and ammonium ion. Like for example, when we have ammonium carbonate, so we have a soluble compound. Or group 1, what are the group 1A elements? That's the first column in the periodic table of elements. Like for instance, we have sodium. So we have sodium carbonate. This is soluble. This doesn't form precipitate. Phosphates are also insoluble except when they are paired with group 1A and ammonium ion. So that's the same rule for carbonate. Hydroxides are also insoluble except when they are paired with group 1A, calcium, barium, and strontium ions. For sulfide, we have insoluble, but when they are paired with group 1A, 2A elements, and with ammonium, they are soluble. For sodium, ammonium, and potassium, they are all soluble. Okay, compounds containing sodium, ammonium, and potassium are soluble, so they don't form precipitates. Another type of chemical reaction is called combustion reaction. So here, an element or compound reacts with oxygen, which produce energy, usually in the form of heat and light. So we have here an example of a combustion reaction. So we have two types of combustion reaction. The first one is a complete combustion. This means that we have enough supply of oxygen. So in the product side, we only have carbon dioxide with, of course, light or heat. Okay. Again, in complete combustion, we have enough supply of fuel, or I mean of oxygen. Okay. So you can see here a blue flame. That means we have a complete combustion. For incomplete combustion, we have insufficient oxygen available. So what happens is that we have carbon and carbon monoxide as our additional products. So you can tell that an incomplete combustion occurs because you have a smoky flame. No? You have a yellow color flame. That's because we have unburned carbon due to the insufficient amount of oxygen supply in the equation or in the reaction. So these are example of incomplete combustion. So these are the two types of combustion reactions. We have our complete combustion. So we have enough supply of oxygen.
So in the products, we only have carbon dioxide and water vapor, whereas in the incomplete combustion, we have lacking supply of oxygen. So we have unburned carbon in the product side. Another type of chemical reaction is called oxidation reduction reactions, or simply redox reaction. Red from the reduction, ox for the oxidation reaction. So this is a chemical change that occur when electrons are transferred between reactants. So when you say oxidation, there is loss of electrons or increase in the oxidation number. Remember that electrons are negatively charged. So for example, when we have a starting oxidation number of plus 4, when we lose 2 electrons, for example, what happens then is the positive number should increase. Okay, so when we lose 2 electrons, we should have a plus 6, right? So there is increase in the oxidation number because we have loss of electrons. Reduction, on the other hand, is there is gain of electrons. So there is decrease in the oxidation number. So for example, when we start with the plus 4 oxidation number, when we gain 2 electrons, because electrons are negatively charged, so this positive should decrease, no? That becomes plus 2 when there is gain of electrons. Okay, remember oxidation, loss of electron, and increase in the oxidation number. Reduction, gain of electrons, and there is decrease in the oxidation number. Okay, so we have here the so-called Leora and Geroa. Leora. Okay, L stands for loss of electrons. This is oxidation. This one is reducing. A stands for agent. Okay, so when there is loss of electron, that's oxidation, and we have the reducing agent, no? Like for example here, so this is a reducing agent. The reducing agent loses electrons. Okay, we have reducing agent losing electrons and is oxidized in the process. Okay, so these are the reactants. Again, the reducing agent loses electrons and is being oxidized. We have an oxidation here. Now, Geroa. We have Geroa. G stands for gain, E stands for electrons, R for reduction, O for oxidizing, and A stands for agent. Okay, so here we have, in the example, we have our oxidizing agent here. The oxidizing agent gains the electrons. Where did the electron come from? From the reducing agent. Okay, the oxidizing agent gained the electron lost from the reducing agent. So the oxidizing agent gained electron, and in the process it is being reduced. Okay, it is being reduced. That is why we have a reduction in here. Again, the oxidizing agent gained the electron from the reducing agent. So it gains electron, and in the process it is being reduced. Okay, that is why A here is called reducing agent, by the way, because it has caused the reduction of B. That is why it's called reducing agent. Oxidizing agent, on the other hand, is called oxidizing agent because as it gained the electron, it has caused the oxidation of A in this example. So we have rules for assigning oxidation number. The oxidation number of monoatomic ion is equal to the ionic charge. When we say monoatomic ion, we only have one atom in the ion. So whatever its charge, that is also its oxidation number. For the oxidation number of hydrogen in a compound, it's always positive 1. For oxygen, on the other hand, it's always negative 2 in a compound. For uncombined element, its oxidation number is 0. For neutral compound, the sum of the oxidation numbers of the atoms in the compound must equal to 0 because we have a neutral compound, so we don't have a charge. So when we add the oxidation number of the atoms in that compound, we should have 0 in total. For polyatomic ion, meaning we have many atoms in the ion, the sum of the oxidation numbers must equal the ionic charge of the ion. Okay, so those are the rules for assigning oxidation number. So, like for example here we have, how do we find the oxidation number of carbon in carbon dioxide? So, we know that since carbon dioxide is a neutral compound, our total oxidation number for the atoms in carbon dioxide should be equal to 0. So, in the previous slide, we know that the oxygen in the compound has a negative 2 um, oxidation number. Since we have a 2 here, so we have, this is the 2 for the 2 oxygen atoms. So, we multiply the 2 subscript here by the oxidation number of oxygen, which is negative 2. So, we have a negative 4. Therefore, to get a 0, the oxidation number of carbon should be positive 4. No? Because carbon dioxide is a neutral compound. When we add again the oxidation numbers of carbon and atoms in this compound, we should get a 0. Since our oxygen atom has negative for oxidation number because we have 2 oxygen atoms, our carbon atom should have a positive 4 oxidation number. Another example, find the oxidation number of sulfur in sulfate ion. So this is an example of a polyatomic ion because we have many atoms in the ion. Again, we know that for polyatomic ions, the total of the oxidation number should be equal to the charge of the ion. So when we add the oxidation number of sulfur and oxygen, it should be equal to negative 2. Okay, so we have 4 oxygen. This is the O for oxygen, and 4 because we have 4 oxygen atoms in here. So we know that the oxidation number of oxygen is negative 2. For oxygen, we have a negative 2. So we multiply that by 4 oxygen atoms, we have negative 8. So what should be the oxidation number for sulfur so that when we add that by negative 8, we get negative 2? That should have a positive, what? Positive 6. Okay? So our sulfur should have a positive 6 oxidation number. So we have a positive 6 here and we have a negative 8. We will get negative 2. Okay, so here we have sodium hydroxide. This is now a redox reaction example. Sodium hydroxide reacting with hydrochloric acid to form sodium chloride and water. Okay, we know that oxygen has a negative 2 oxidation number. So we have, and for hydrogen in a compound, we have positive 1. Okay, so therefore, okay, sodium hydroxide is a neutral compound. So we have a negative 2 and a positive 1. What should be the oxidation number for sodium for it to be 0, which it should be positive 1. Okay, 1 minus 2 is negative 1 plus 1. We have a 0. Okay, we know that hydrogen oxidation number is positive 1 for in a compound, I mean. So therefore, chlorine here should have a negative 1. Okay, so we have a negative 1 for chlorine, therefore we have positive 1 for sodium. And we have positive 1 again for hydrogen. Since we have 2 hydrogen atoms, so it's positive 2 all in that compound. And we have a negative 2 for oxygen. Again, since they are neutral, all of these compounds are neutral. When you add all of them, you'll get a 0. Okay, 2 plus negative 2, you also get a 0. So we have magnesium, by the way. Is this an example of a redox reaction? Is there gain and loss of electrons? Sodium in the right side, we have positive 1. It's still positive 1 in the right side. Oxygen has negative 2 on the left side. On the right side, we also have a negative 2. So there is no gain or loss of electrons. Hydrogen has plus 1 on the left side. On the right side, we also have a positive 1. Same with chlorine. So we don't have a gain or loss of electrons di ay dire. No? Another example. Therefore, kung wala gani gain and loss of electron, that means that is not a redox reaction. Okay, so there should be gain and loss of electrons. You can tell that because the oxidation number of that certain element is changed, no? It has either decreased or increased depending if it's gaining or losing the electron. So let's have another example. We have magnesium reacting with hydrochloric acid to form magnesium chloride and hydrogen gas. So for magnesium here, since it's an uncombined element, that means its oxidation number should be 0. Meaning, when you say uncombined, it's alone. It is not combined with another element. No? So its oxidation number is 0. We know that hydrogen in the compound has a positive 1 oxidation number. Therefore, since hydrochloric acid is a neutral compound, our chlorine here should have a negative 1 oxidation number. Okay, so we know that that chlorine has negative 1 oxidation number since we have 2 chlorine atoms. Therefore, in the compound, we have a negative 2 for chlorine. Since magnesium chloride is a neutral compound, our magnesium should have a positive 2 because when you add positive to a negative 2, you'll get a 0. Hydrogen here, on the other hand, since it is an uncombined, no? It's uncombined, so it should have a 0 oxidation number. So now, let us compare the oxidation numbers of the elements in the reactant and on the product side. Let's see if we have now a gain or loss of electrons or if we have a redox reaction. So as you can see here, in the reactant side, our magnesium has 0 oxidation number, whereas on the product side, it has now a positive 2. That means, what's happened? Did it gain or lose electron? When the oxidation number is increased, that means there is what? There is loss of electrons. Again, because electrons are negatively charged. So the oxidation number should have increased. So from 0 to 2. That means it has lost 2 electrons. And there is oxidation. No? When there is loss of electrons, there is increase in the oxidation number. There is oxidation reaction. And magnesium, therefore, is reducing agent. Again, we have, what is this? Leora. Leora. Loss of electron, oxidation, reducing agent. Okay? Remember that. So when we have oxidation reaction, we also have a redox reaction because redox reactions go hand in hand. No? When there is reduction, there is always oxidation reaction. So when magnesium lost that electron, so 2 electrons, some other element has gained that electron. Okay, in this case, it is the hydrogen that's gaining the 2 electrons. Okay, so therefore, we have reduction for hydrogen. No? Na-reduce siya, meaning na-decrease ang oxidation number from positive 1 becomes 0. We have gain of 2 electrons because we have 2 hydrogen atoms. No? So you have plus 2 becomes 0. Because we have 2 hydrogen atoms. So hydrochloric acid then is the oxidizing agent. Again, we have a GEROA. Okay, gain of electrons, reduction, we have oxidizing agent. Another example, we have permanganate ion reacting with sulfurous acid to form manganese ion and bisulfate ion. So we know that oxygen has a negative 2 oxidation number. Since we have 4 oxygen atoms in this ion, so we have a negative 8. We have negative 2 times 4 is negative 8. Since this is a polyatomic ion, the sum of the oxidation numbers of the atoms in this ion should be equal to the charge of the ion. In this case, the charge is negative 1. So, when we add the oxidation number of the atoms in this ion, we should get a negative 1. Therefore, the oxidation number of manganese should be positive 7, because when we add 7 and negative 8, we get negative 1. Okay, for the sulfurous acid, we know that hydrogen has a positive 1 oxidation number. Since we have 2 hydrogen atoms, we have a positive 2 total for the hydrogen in this compound. For the oxygen, we know that it's negative 2 since we have 3 oxygen atoms. So we have a negative 6 total for the oxidation number of oxygen. Since sulfurous acid is a neutral compound, when we add the oxidation number of all the atoms in here, we should get a 0. So we have, what should be the oxidation number for sulfur in here? It should be positive 4, because when we add 2 and 4, we get a 6. Minus 6, we have 0. Okay, so the oxidation number of sulfur should be 4. On the right side of the equation, we have our manganese ion. Since this is a monoatomic ion, meaning we only have one atom in the ion, its oxidation number is equal to its charge. Since its charge is positive 2, of course, its oxidation number is also positive 2. So for the bisulfite ion, this is a polyatomic ion, so the total of the oxidation numbers of all the atoms in here should be equal to the charge, which is negative 1. We know that hydrogen is positive 1. We know that oxygen has negative 2 oxidation number. So since we have 4 oxygen atoms, its total oxidation number here is negative 8. Okay, so what should be the oxidation number of sulfur? It should be positive 6, because when we add 1 and 6, we have 7. Minus 8, we have a negative 1, which is equal to the charge of the polyatomic ion. Okay, now let us compare the oxidation numbers. For oxygen, it's the same, no? Negative 2 on the reactant side and negative 2 on the product side. For hydrogen, it's still the same, positive 1 on the reactant side and positive 1 on the product side. What was changed? What were changed were the oxidation numbers for manganese and sulfur. For manganese, it has reduced from positive 7 to positive 2. So we have gain of electrons. No? When the oxidation number is decreased, that means electrons are being added or gained, no? Because electrons are negatively charged. So of course, the positive or the oxidation number should decrease. And in the process, there is reduction, okay? So when the oxidation number is decreased, we have reduction. We have gain of electrons. And permanganate ion then is the oxidizing agent, okay? We have what? Gain of electrons. So GeROA. Gain of electrons, reduction, oxidizing agent. Sulfur, on the other hand, look at the oxidation of sulfur, it has increased. So there is loss of electron or oxidation, and sulfurous acid is our reducing agent. Okay, Leora, loss of electron, Leo, oxidation, reducing agent. Okay, so this is oxidation reduction or redox reaction.